My name is Dr. David Bengtson-Esgrelli, and in this video I will present a framework for predicting dengue cases using publicly available data and machine learning. The framework is called the Dengue Climate Nexus XGBoost Multi-Model Framework, abbreviated the Dengue-X framework. It is a byproduct of early warning system development research, where the research rationale was given that dengue transmission is a system, then high-resolution insights into that system could be leveraged in intervention design, intervention targeting, and mobilization. And this would then in turn bolster those interventions and their relevance, coherency, efficiency, effectiveness, sustainability, and impact. If we can fully understand the dengue system, then we can get closer to the WHO's 2030 goals of near zero mortality of dengue and also reducing the incidence. To accomplish this, we must map what drives dengue. This means quantitatively and qualitatively understanding system inputs and the extent to which inputs interact to impact incidence. However, the dengue system is not simple, and it requires a multi-theory, multi-model approach. We need to understand the extent to which the system is or is not dynamical, deterministic, stochastic, bifurcatory, chaotic, etc. For example, whether some inputs and input interactions follow superposition principles, while other inputs in the same system may be better mathematically observed with nonlinear differential equations. The theoretical answer to this set of questions will guide what equations and what math models we need to use. In turn, this will result in better predictive accuracy, and that could then translate into more accurate interventions and substantiated policy decisions. A short example before we start. Imagine a large multi-biome nation that has significant geographic and topographic heterogeneity. So while precipitation across this country might be about the same, the soil types lining ephemeral bodies of water might alter water permeability, percolation, and ultimately runoff. And so this difference, which might be present across that nation, could be the difference between standing water in one region and a dry pond bed in another. Thus, the impact that precipitation has as a driver for dengue may be to a currently unquantifiable extent dependent on several additional inputs. So this research area aims to understand, quantify, and target these kinds of input dynamics. Today, we're going to focus on the nonlinearity and the threshold dependency within the dengue system, and how to quantitatively and qualitatively characterize this, and how to find actionable insights that can be used for early warning system development. One thing first, to run this analysis, I initially ran and modified Python scripts in PyCharm. However, to streamline the data extraction, transformation, and loading process, and to standardize the data analysis itself, I designed 3 bespoke applications, the same effectiveness with improved efficiency. These apps can be made available should there be public interest, and you can contact me at the email made available in the description. All right, so let's take a look at the actual framework. To visualize this process, I've made this flowchart. There are 4 main steps. Steps 1 and 2 deal with collecting input and output variables. Step 3 deals with using the Dengue-X application to run the analysis. And step 4 provides suggestions on how to use these findings. All right, so let's start with step 1. Navigate to the Pan American Health Organization website. It's linked in the description as well as in the flowchart. The title should say Dengue Data and Analysis. Once you're there, scroll down and you'll see analysis by Americas, subregion, and country, where you click on country. After this, you should be in the Cases tab. In the Cases tab, navigate to EpiCurve, the EpiCurve subtab, where when you click on that, you should see the option to filter by country and by year. We will be filtering for Ecuador and for the entire available temporal period. With that selected, go to the columns where the years are available. Click on the first year, then hold down left shift, and then click on the last year. When you hover over the columns after highlighting them, you should see a dialog window kind of opening up, and click on the View Data icon. This should open the View Data window, and from here you should be able to click on Download All Rows as text files after which the text file should be downloaded as a .csv file available in the Download tab of your browser. This text file should be named something like WEPICurve data, and you can open it very quickly just to take a look and see that it is of the correct country and temporal period. But you will also notice here that this text file is in a particular convention here. You can see the country, year, epi, week, new cases. This format is not really the format that we want, so we're going to use an application to convert this. From here, we open the CSV converter application. We select the correct CSV file. That would be the one that we just downloaded. We then choose the destination that we want it to be, where we want the converted version to be stored. Once we've selected the CSV file, the country should be automatically selected. However, if it is incorrect, we can change that manually here, and then we can change the output name as well. After this, we click Generate CSV, and after a few moments, that file should be stored in the output destination. At this point, we would be at step F, and that concludes the first step of this process. This brings us to step 2. So to do step 2, you need to register a Google Cloud project, and you then need to enable Earth Engine API, and then register that project. You can register a non-commercial project for free. This will give you 150 Earth Engine computation units per month. This would be enough to run this type of analysis for about 15 countries. The next step involves opening the Climate Extractor application. From here, you would write your Google Earth Engine project ID and then click Initialize Earth Engine. Once you've done this, you should see in the little text box below that 284 countries have been loaded and that the Earth Engine project has been initialized. From here, click on Select Dengue Weekly CSV, and in this section, select the CSV file that was generated from the previous application, and then choose the destination that you want this new climate file to be stored in. Next, ensure that you have the correct country labeled, and then select the output name that you want. And after that, you can click Run Analysis. The download should take 2 to 3 hours, and you can see the download process in the application window. Once that file has been downloaded, it should be stored in the destination output folder, and you would have completed step 2. Now that we have the Dengue variable and the climate variable files ready, we can go ahead to step 3. Here we're going to open the DengueX application. Once we've opened the DengueX application, you should see button tabs at the top of the application window. The first step would be to load your WI file. To do that, click on the button that says Select WI file, and then click on the file created at the end of step 1. The next would be to load your X file, and this would be done by clicking on the Select X file button and then selecting the file generated in step 2. Once both are loaded, click on Advanced Calibration. In this tab, when a dialog window should be opened, here you select the variable column name and select which independent variables or X features you want to include in this particular analysis. The flexibility here allows us to extract climate data files with many different variables without being locked into using all of them in every single analysis. For example, we can see here that we collected normalized differentiated vegetation index, but since many of them are missed weeks here, indicated by NAN, we will exclude this one from this analysis. After this, click Apply. Next, we will configure lags. So since climate conditions often have a delayed effect on dengue cases, we apply lags to kind of simulate this with the analysis. So click in this window, Detect Lags, and this is going to use cross-correlation to find the optimal lags. From here, we can manually adjust these lags. I recommend making them all positive numbers. I've also included the option of tweaking the hyperparameters here, but today we're going to keep it simple. Then when we're ready, we hit run analysis. While we wait, I'm just going to reiterate some points. When we discuss the y variable, this is basically the dependent variable. In our case, that is dengue cases. The x features, these are the independent variables. And in our case, these are climate variables. Y hat is something that's going to be coming up in this section. That is the predicted dengue variable. Essentially, for a given time t, the model will try to predict a version of y, and that is called y hat. With that, let's take a look at what we have. All right, starting at statistics. In the statistical analysis tab, we have several subtabs. The starting one is the y variable subtab. On the left side, we have the table of the descriptive statistics for the y variable. And we can see the mean, standard deviation, minimums, maximums, medians, etc. And on the right, we can see the time series analysis of it. This is a good opportunity for us to compare the time series analysis that we see here with the one that we saw on the Pan American Health Organization website, just to make sure that it is correct. Next, we have the X feature subtab. So these are the descriptive statistics of the individual X features that we collect through the climate extractor application. Again, on the left side, we have the descriptive statistic table for each one of the variables. And on the right side, we have the time series analysis as well. Note that in this section, we can observe and calculate any changes in climate variables across the temporal period. Next subtab looks at y versus x, and these are the comparative statistics for the y variable against the each of the x variables. So we have the Pearson and the Spearman correlation coefficients. An important note here, and noted throughout the literature as well, is the weak correlation, or I guess the relative weak correlation between y and x variables. This speaks to the non-linear relationship between dengue cases and climate features. The last three subtabs in this section look at y hat statistics, specifically y hat versus x, y versus y hat, and then y hat itself. Next, we have the XGBoost analysis. Here you will see MA1 and MA2, which stand for Model Approach 1 and Model Approach 2, respectively. MA1 is a climate-only model, which means that it only uses climate features as inputs. In simple terms, MA1 has a training period and a testing period. The training period is when the model gets to see, quote-unquote, y variable values for a given time t, and gets to see the x features for that same time t. From this, several small equations or formulas or algorithm components are made. When the training period is over, the model will keep these small equations. The model will then use these during the testing period. In the testing period, the model will be given time t, and it'll be asked to fill for that time t a y hat. In Model Approach 1, all the model has access to are those several small equations and climate variables for that time t. So it will use the formula and input climate variables and then receive an output. This output is the y hat prediction. And so in theory, it is sort of like plotting y using an f of x formula. In Model Approach 2, the same is true. But in addition to climate variables, the model gets to see, quote unquote, the y for the previous temporal unit. This allows the model to be informed by the disease trend dynamics. Notably, this is similar to how statistical models such as ARIMA currently do disease prediction. However, I have found that on the task of generating y hat using autoregressive dengue case data, ARIMA results approach the average y, whereas XGBoost significantly better. With that, let's take a look at the XGBoost analysis. So in the first subtab on the left, we have a table. We have mean absolute error, root mean squared error, and R squared. These metrics are standard for evaluating model performances. Note that non-autoregressive models should have a negative R squared, which we actually see in this analysis. On the right, we have the y versus y hat time series analysis. For both time series analyses, the full blue line is the y variable, the orange dotted line is the predicted y hat variable, and the vertical dotted blue line is the split between the left side, training, and the right side, testing. This is a good moment to pause when looking at model approach 1's time series analysis and ask yourself, is this model response accurate in relative terms? Is the prediction precise? Consider the usefulness that an inaccurate but precise predictive signal can have for early warning system development. And in addition to that, consider the fiscal efficiency of a predictive model that doesn't require autoregressive disease data. Simply put, the best case scenario is knowing exactly how many dengue cases will be occurring in a given time t. The second best case scenario is knowing the magnitude relative to the historical dengue cases that a given time t will see. That is what model approach 1 gives us. The next subtab, y versus y hat table, has each temporal unit and the corresponding y and y hat variable. Note that this whole table is highlightable and it can be copy and pasted. This brings us to the SHAP analysis subtab. We first have the B-swarm plots. This uses cooperative game theory to assign the most contributory X feature. The top feature is the most valuable and the bottom the least valuable. Note that for MA2, the lagged dengue variable is almost always the most valuable X feature. Next are the 2D dependency plots. These allow us to quantitatively identify discrete climactic ranges that correspond to elevated dengue cases. These are the climactic Goldilocks zones. Out of all of the findings, these are directly and immediately useful for early warning system development. This is because they allow us to identify climactic ranges that are associated with elevated dengue risk. Particularly if paired with longitudinal weather forecasting, we can use cataloged climactic Goldilocks zones to identify high-risk climactic patterns before they occur. Additionally, if dengue surveillance data is tagged with latitude and longitude data, we could use point geometry to catalog high-risk climactic patterns by subnational regions. This would be very useful for targeted intervention mobilization, but it would also have the added benefit of facilitating subnational geospatial analysis. Okay, let's take a direct look at the 2D dependency plots that we have generated. Starting with mean temperature for model approach 1, we can see a discrete rise after about 21 Celsius, reaching a peak at around 21.5. If we then move on to max temperature, we can follow the rise to about 23 Celsius, and then it dips after 24. This would suggest that the optimal range for dengue in Ecuador is somewhere between 21.5 Celsius and 24 Celsius. This is in stark contrast to some other regions, specifically in the Caribbean, where the optimal range for dengue is closer to 27.8 Celsius. Next, looking at relative humidity, we can see that the threshold appears to be trimodal. The extent to which this is quote-unquote true or an artifact is unsure. However, we can see that the second positive range indicated by the red dot is specifically between 86.55 and 87.31. And we see a very discrete, sharp sort of threshold here. Next, let's take a look at precipitation. We see that between 0 and 60 millimeters per temporal unit, the value stays below 0 SHAP value. This is the impact on the dengue risk. After 60 and between 60 to a little bit over 100, the value becomes stably positive, indicating elevated dengue risk and also indicating a climactic threshold of about 60 to 100 millimeters per temporal unit. Notably, 2D dependency plots are also available for model approach 2. However, the heavy weight of dengue cases as an X feature has a distorting effect on the remaining X features. Finally, we have the equation tab. So on the left, we have what is labeled as MA1 equation plus metadata. So this is essentially a piecewise formula, and I'm going to explain what that means. When we train XGBoost, it learns many specific small decision trees. So a tree is conceptually, for example, If temperature is less than 27.3, go left. If temperature is greater than or equal to 27.3, then go right. Following this, we might also have if rainfall is less than 5, then the output should be plus 2.1. Or we might have if rainfall is greater than or equal to 5, then output should be minus 0.8. So a single tree at this point could be if temperature is less than 27.3 and rainfall is less than 5, then output should be minus 0.8. If temperature is greater than 27.3 and rainfall is greater than 5, then output could be plus 2.1. So XGBoost builds hundreds of trees, and with each tree it adds a small correction. Then a base score is added, and this informs the y-hat at time t given input for that time t. This piecewise formula is how the input ranges contribute to changing the output for a specific model trained on this specific data. However, if we assume that the formula found is based on an actual relationship between input and output, then if we look at climate data from a future period, the dynamics between input and output should be similar, unless a new unseen threshold occurs. But assuming that that hasn't happened, we would then be able to use longitudinal weather forecasts to get a relatively accurate y-hat prediction. And so on the right, this piecewise equation is showed in a time series. So in this testing period, we see that the black line is the dengue cases, or Y, then the blue line is the y-hat from the previous XGBoost analysis tab. Here we also have the equation y-hat, and this is the y-hat prediction using only this piecewise equation that's on the left. You'll notice that it is of a lower amplitude than the blue line. The reason for this is that the blue line has a built-in base score amplifier that the green line does not have. However, ignoring the global amplitude blunting of the green line, we can see that, first of all, green and blue lines approximate one another. And in addition to this, green and blue lines also approximate the actual dengue value as well, albeit relatively and not absolutely. This brings us to the final point. Can the piecewise equation that worked well during the testing period produce a relatively accurate equation y-hat forecast if we input future climate data? If the answer to this is yes, then this framework could successfully forecast dengue magnitude using only climate variables and historical dengue case data for training. The bottom right window, labeled MA1UX file, allows us to input a new future X-feature data set to test this theory. Specifically, the intention is to employ subseasonal to seasonal data. Importantly, new X-file data must be of the same data type and format as the data that the piecewise equation was modeled on. To conclude, this framework provides significant insight into the dengue climate nexus. It streamlines descriptive and comparative statistics and also provides quantitative performance metrics in mean absolute error, root mean squared error, and R squared, along with time series plots that can be used for model approach evaluation. It also facilitates shaft-based feature attribution in the B-swarm plots and also identification of discrete climatic thresholds with the 2D dependency plots. The framework also supports longitudinal dengue forecasting using subseasonal to seasonal data in the equation tab. The application itself also supports image downloading for report generation. While this framework and application look specifically at nonlinear threshold dependency in the dengue climate nexus, ongoing developments include the integration of compartmental epidemiological models, Makarov-chain Monte Carlo methods, the addition of additional tree-based supervised learning approaches like LightGBM, and the inclusion of statistical time series models like ARIMA and SARIMA. Thank you for listening, and please refer to the description tab for additional resources.